Good morning, everybody. Thank you so much for attending our January Builder Forum series on ventilation and step code. That's today's session is presented to you by the Township of Langley Green Buildings Department and Focal Engineering. And we are thankfully sponsored by BC Hydro and Fortis BC. And our credits are supported by AIBC and BC Housing. So without further ado, okay, what's on the menu today? We got some exciting reminders and updates from the township. I'll be talking a little bit about step code and some new incentives. Jean, our building specialist, will give us some tips and tricks for our compliance. Sarah Maleska will lead us through an exciting polling exercise. Then we'll get to our presentation of the day. It's on ventilation and step code. And we'll promptly close and let you get on with your day. I want to highlight here at the bottom of the screen, we're not doing our polling just yet, but to make our transition a bit smoother, please grab your cell phone soon and type in a browser menti.com, that's menti.com, and there's a 6-digit code. I'm going to have this note here on a lot of slides, so don't worry if you don't do this right away. You don't have to memorize it, but please do that sooner than later so we can have the polling go smoothly. I also want to highlight, if you have any questions throughout the presentation or comments or any of that kind of good stuff, please use the chat. It's somewhere going to be in your screen. Sarah, could you, I can't see the chat. Could you let me know where that is? Or let the gang know where it is?
I think in the bottom right of your screen, you can click on chat and it will come up on the right side for me, and then you'll have the main presentation in the middle.
Great. Okay. So thanks, Sarah, for that. So use that the chat box for questions and comments and that kind of good stuff. Okay, a bit of a recap. We had our last Builder Forum series in November, and that was focused on air tightness and heat pumps. The takeaways there were for air tightness, that air tightness is a component of step code, and as municipalities ratchet up their step code requirements, so will your air changes per hour targets, or those will get smaller. So this is what we learned about at our last session. Some of the major takeaways: you need to plan from the start, work with your trades, and very importantly, you should also be taking advantage of mid-construction blower door testing. And here at the township, we are still we are still incentivizing that. And we also talked about heat pumps, and heat pumps are going to be a very, very common technology you're going to be hearing about soon and in the future. Heat pumps will be important for meeting the upper steps, some critical points outside of energy targets and compliancy pieces. We really want to ensure that this technology works as expected with predictable operations. So please look into how heat pumps are meant to be working. And when sizing and designing around heat pumps, you want to take a holistic design. So sizing will be critical to successful and predictable operations. That being said, if you were not at our last Builder Forum series on air tightness and heat pumps, I'll show you how to find our recorded version of that. Please go to tol.ca, click Add Your Service there on your left, find yourself to the Building Development and Engineering section, find the BC Energy Step Code section under Buildings, or you can simply type in tol.ca/step code in your browser and you'll find your way to this page here. And this is our page where we have all our interesting information on step code around compliance, documentation, and as well, if you scroll somewhere near the bottom, you'll find your way to our education section where you'll be able to find our previous education series going back some time with the videos, the slides, all the good stuff there. So if you want to recap or learn more about air tightness and heat pumps, please visit this page and you'll be able to find it there. Bit of a reminder, and as noticed or noted last year in November, it is 2021 now, so we are regulating step 3 for residential buildings in DP areas. Outside of DP areas, we are still at step 2. Come 2022, we will be unified, and through the DP and non-DP, we'll be requiring step 3 for residential buildings. I'll pass it off to Ajeen for our compliance notes.
Thanks, Kevin. Hello, all. I just want to keep this super short. So I've been reviewing the building permit submissions for like energy compliance and came across certain gaps that I would like to fill it in today. So for all BP submissions, just make sure you submit all the documents. That makes it easier for us to review and like fewer requests for documentations, right? It can also help you reduce your processing times. We will be updating our website pretty soon, and also we have to update a updated building permit application checklist. So this will be also done pretty soon. Keep a track of our website like tol.ca/step code. It will be updated pretty soon. Next slide, Kevin. So yeah, these are the documents what we are looking for. Like if you can see, the first one is like building energy, a BC energy intensity report. So this is a TOL document, and you can find that in our website. So please complete them and also make sure it's been signed by a professional engineer. Now the part 3 energy design report. So that's basically a provincial document, and it's been out since I think September. And so please make sure you submit that too. Also, I've been receiving documents, I've been said like this is the building envelope performance, but there's no supporting documents. So we want to make sure like how the effective envelope performance is being derived. So please make sure you submit your thermal bridging calculations. It could be either the BC Hydro calculator or like any analysis what you're doing. Energy modeling report. Yes, I've been receiving this one. So yeah, just want to keep it there. And energy statement on drawings. So I've been receiving documents like drawings without energy statements, and also sometimes the wrong energy statements. So just make sure you do it right. If you have any questions or difficulties, like you can refer to this document like whole building energy modeling service guideline. That's by AIBC. So you can have a look at that. You can also get an idea of like what should be included in an energy modeling report. Next slide, Kevin. So this is just a reminder for all the energy modelers and energy advisors. Use Abbotsford weather file. So just use Abbotsford weather file. So just make sure you check that one. And Part 9 buildings in Langley, make sure you use the latest version of the energy compliance report. So that will actually help you with if you have a multiple residential buildings, you can break down unit by unit. And also make sure you have the heating degree days that's set to 2700. This is as per BC building code. So we want to make it consistent throughout all the submissions. So, and it's going to be easier for us to review too. Now, I think we mentioned this one in the last Builder Forum series. This is for the section F of compliance form. We now require you to complete that part. This is basically the GSG, and there are some details over there. So we just want to track it. The last part 3, passively cooled buildings. We have been receiving submissions which refer to later versions of ASHRAE 55, 2013 and 2017. So as per Vancouver modeling guidelines, they refer to ASHRAE 55 2010. So make sure you refer to the same standard as well, just to make it consistent throughout the industry. Again, when you do the passively cooled buildings, make sure the Abbotsford weather file is used. Yep, that's it from me. And if you have any issues or something, you can just email it to us. You can get in touch with us. Yep, we will have an email address towards the end of the presentation. Thanks, Kevin. Thank you all.
Thanks, Ajeen. And just a reminder for folks on the phone, please grab your cell phones and type in menti.com and use this number 269757. We'll be polling shortly. So a bit of some updates here in market. A few slides ago, I talked a little bit about heat pumps and that being a likely technology to help meet policies where you're building. The government has recognized that to help transition this technology to the public, they've made a very generous incentive program that's relatively new. I should also highlight, it's really important that you acknowledge this, it's not going to be around forever. There are significant incentives when talking about step code heat pumps for new construction. This is focusing on upper steps electrification. You can also stack this or combine this with the Green Building Rebate Program from the Township of Langley and together come out with some very, very large incentives. A couple examples I'll do real quick. You decide to build a single family dwelling. You decide to choose to build to step 5 directly. That's worth $10,000 as a rebate directly. You'll get an energy advisor rebate, which you need to hire one anyhow. Now, this person who's building to step 5 decided to build their building all electric, which means there's zero gas running to the building. The all electric is a bonus. You don't have to do this, but if you do this, that's worth $4,000. Stacking that with the existing Township of Langley rebates that we already have, you can get a total of $17,150 by building a step 5 all electric single family dwelling, which is quite significant. We have a second example. This is for a 4-unit townhouse building. You decide to build not to an upper step, but to whatever the municipality is calling for, if it is lower than 4 or 5. And you choose to take the heat pump path, where for each of those units, you use a combined space and water heat pump. That's for your space heating and domestic hot water. You take advantage of the energy advisor rebate and our Township of Langley rebates, and you will come out with a total rebate of $20,500 for the 4-unit townhouse building. So as you can see, these are very, very significant rebates. If you want more details, feel free to reach out to us. Again, we have the poll coming shortly. I'm highlighting our next Builder Forum series here. Come March 23rd, our following session is going to be on fenestration and building performance, where we'll be focusing on cost-effective high-performance fenestration systems. We'll be talking about fenestration and thermal comfort. That's going to be a key word you're going to be hearing very often as well, and that's really focusing on overheating. And we'll be talking about lessons learned and best practices for design and install. Keep your date open for March 23rd. Shout out to our friends at the City of Abbotsford who are holding their own webinar series starting the next sessions on February 23rd from 9 to 11, and it's co-hosted by CHBA. You'll also be able to receive credits by attending. It's focusing on step code metrics and rebates through Abbotsford, so please attend that. Alert coming soon. This should be on everybody's radar. The Township of Langley is exploring adopting step code for Part 3 non-residential buildings. Currently, only residential buildings are regulated by step code here at the Township, but we're exploring this. Consultation is coming soon. Please keep your eyes open for any correspondence that's asking for feedback. We really appreciate your input while we develop our non-residential step code schedule. Big news here at the Township. The council had unanimously approved our climate action strategy from our sustainability department just yesterday. This is a big success for the Township. Buildings themselves are a big chunk of the carbon emissions pie here in Langley. It would be safe to bet that we should be anticipating building policies that are aligning with the climate action strategy goals, which focuses on reducing energy, reducing emissions, and also adding renewables to our portfolio. We're anticipating come 2030 our new buildings will be zero emissions, and we're also targeting our existing buildings to reduce emissions to zero as well. For more questions, feel free to reach out. I'm going to pass it over to Sarah for our polling. I hope you're all ready for with your cell phones.
Okay, hi everyone. So to help us wake up a bit this morning, if you're not already awake, can you see the Mentimeter screen, Kevin?
I can. Yes, yeah.
Okay, great. So hopefully on the past slides you saw the code, but if you haven't, you can go to menti.com and use the code 269757. So the first question is, where are you watching from today? Just a little icebreaker to see where all of our attendees are from. Wow, lots of people have already answered. So this is like a heat, or it kind of shows what answer is being said the most. So we have Langley and big, Surrey is slightly smaller. Someone said office, home office, Steveston. Yeah, lots of different locations people are calling in from today. Great, thanks for answering, everyone. The next question is kind of gets our brain going on today's topic, ventilation and step code. We've had 69 people, or 71. Great, that's about half of you. So thank you for participating. The next question, which requirement of the step code does ventilation affect the most? So hopefully after this webinar, you all will get the most right answer, but we will see. So we have 25, airtightness is winning. 46 now. Great, 58 people. Airtightness is winning by a long shot with 39. We have 11 for Teddy and 8 for Mui or Tui. And Teddy, if you don't know, is thermal energy demand intensity, and Mui and Tui are mechanical energy use intensity and thermal energy use intensity. So we have 59 who have answered. I'll wait a couple more seconds. 3, 2, 1. Okay, so we have airtightness on top. Great. Kevin, do you want to share your screen again? Or
Yeah.
Yeah, share the screen and then I'll talk about the next slide. And so you'll find out the answer in the webinar, so you have to stay. Okay. So after the webinar, as most of you have attended before, will know that we usually send out an email asking for your feedback on our event. So this is just some of the feedback that we heard about our November 19th Builder Forum series. You can take a look at it. We also have this information on our website, tol.ca/stepcode. And yeah, you can see that people learned a lot during the webinar and some people were somewhat satisfied. So we use this feedback to help us improve. So we really appreciate you all taking the time to fill it out. And the invitation for this webinar's feedback survey will come out before the end of the day today. Okay, thanks.
Thanks, Sarah. Okay, we're relatively on time, so that's great. So without further ado, I'll introduce Focal Engineering. So Focal Engineering is made up of Susan McDougall and Wes Bowley here today. Susan's a mechanical engineer with over 15 years of industry experience. She sits on several step code committees related to energy modeling and step code. She's the principal at Focal Engineering, focusing on energy efficiency, reconstruction, and retrofits. I will Focal, why don't you share your screen and you can go over.
Sounds good. I'll get my screen sharing, and just while I do, can everybody hear me okay? Getting some thumbs up. Excellent. So I'm going to move the WebEx screen over to the side so I can't see it anymore. Excellent. Okay, so thank you so much, Township of Langley, for hosting us today and for the intro. It was great to hear too all the climate leadership sort of things that you guys have on your plate. So hopefully we'll get some projects in the Township of Langley soon. Just a quick note to everyone. I apologize. I am getting over a bit of a cold, so you may see me sipping on tea throughout the presentation. So I hope that's not too distracting. As Kevin said, my name's Susan McDougall. I'm a principal here at Focal. We're an energy modeling firm in Victoria, BC, but we work across Canada doing energy modeling, energy upgrades, all sorts of things. And thanks to my colleague Wes, who helped prepare the material today and is here just in case for some reason my technology goes down. So we've modeled over 75, coming up on 100 step code buildings in the past. So we're really looking forward to sharing some of the successful ventilation designs and strategies we've seen today, along with some of the things that we've seen that have tripped up some of our projects. So hopefully we can all kind of learn from those shared stories. So just a quick overview of our agenda for the day. We've got intro. We want to do a really quick background on the step code and ventilation, just to kind of highlight a few of the key terms that we'll be using throughout the presentation and make sure that we're all on the same basic page for that. But what we really want to focus on is the interaction between ventilation and step code. Where does ventilation have the most impact? So that goes to Sarah's poll that she showed you earlier. And then, like I said before, we're going to talk a lot about some key design strategies that you can consider for Part 9 and Part 3 buildings, and a few other design considerations when you're thinking about ventilation design and construction in step code buildings before we wrap up. So our focus for today is on Part 9 and Part 3 residential buildings. We'll touch briefly on a few other commercial ones that fall under the step code, but that's just a little slide here or there. Like I said, the focus is really on sort of the interaction between ventilation and step code and presenting some successful and cost-effective design strategies and tips. So our really brief intro to the step code, you saw a very similar slide to this that Kevin was showing earlier. I'm just going to turn my laser pointer on here so you can see the little red button. The reason we showed this particular chart is that it covers both Part 9 and Part 3 steps within the residential sector. So when we talk about step code, you'll hear us use the term upper steps and lower steps, and those can sort of mean different numbers depending on whether we're talking Part 9. Upper steps are usually referred to as steps 4 or 5. Part 3 wood frame are more in the step 4 category, whereas Part 3 concrete often encompasses both steps 3 and 4. The lower steps, of course, are either 2 or 3 below that, and step 1 is, from an energy perspective, generally considered roughly equivalent to current building code. Even though there's more reporting requirements and airtightness testing requirements, from an energy perspective, it's roughly considered the same. The other thing we wanted to just remind folks, which probably are already pretty comfortable with, is that Passive House is considered an alternative compliance path for the highest step. So for Part 9, that would be step 5. Part 3, that would mean step 4. And we're not really getting into Passive House strategy or Passive House in any sort of detail today, but there are a couple of good strategies that we can borrow that we see on a lot of Passive House projects. So we wanted to just raise those as things that you might want to consider if you are targeting those highest steps, because they have seen some success in BC. And then just a quick reminder on the metrics that are seen in the step code and the definitions, which we've shown below the table. So now we've got Part 9 here across the top and then Part 3 across the bottom row. So both have an air tightness metric, that's this first column here. They are described a little bit differently, but we're not really getting into the details of that. It sounds like you guys talked about air tightness a lot in November. So today we'll be focusing more on these two. There's a metric for equipment and systems. So in Part 9, you actually have an alternative. There's a % better than a reference building as described by EnerGuide. Or there's the mechanical energy use intensity, which we refer to as MUI. And just over the course of this presentation, just for keeping things short, I generally talk about either MUI or TUI rather than adding in the or % better than reference. So I'm not excluding this by any means. Just know that when I say MUI, I'm basically saying one of these two alternatives. And then for Part 3, the equipment and systems metric is the total energy use intensity. So it encompasses a little bit more than what the MUI does in the Part 9. Both Part 9 and Part 3 have the TEDI metric, which is the thermal energy demand intensity. And then as Ajin alluded to a little bit earlier, there's an overheating metric for passively cooled buildings in part 3. And again, that's not really the topic of today's conversation, but that is one of the metrics to keep in mind. So that's the total amount of overview we were going to give, just making sure everyone's comfortable with really the acronyms that we'll be using. If you have more questions, though, we're told that Gene's a great reference, so you can reach out to him if you have more questions about how some of those may be calculated or interpreted. Okay, so now for our quick overview again on ventilation, and just zooming way out, what we're talking about from ventilation is really an airflow requirement, an outdoor airflow requirement in buildings. And typically this is required for occupied spaces. So whenever you are going to have people present in a space, you need to bring in enough air for them to be able to breathe and also just keep the space fresh. Sometimes there's also exhaust air requirements. So in spaces where you might have pollutants, a parkade's a really good example where you're going to have carbon monoxide buildup from cars, but also interior spaces like janitor rooms, mechanical rooms. Those might also have, excuse me, exhaust air requirements as well. So we'll use the term outdoor air or OA and exhaust air to talk about those different requirements to a space or from a space. And usually these requirements show up as a flow rate. So how much volume of air do you have to either put into a space or remove from a space over a period of time? Usually we see in buildings that this is delivered via mechanical means. So, a rooftop unit, an air handler, fans, anything that's kind of mechanically pushing air into a space or pulling it out. But there are also passive alternatives, so sometimes windows, or sometimes we see exhaust-only scenarios where you just are exhausting from a space and air is kind of trickling in through the envelope or whatever other means you might see. And just ventilation in general, how does it have an impact on buildings? Well, obviously it has an impact on energy consumption, especially in the wintertime when we have to heat that outside air up to the internal space temperature. So that's kind of where it really plays a role in the step code, is in energy usage. But there are some other considerations we have to think about, like thermal comfort and envelope performance as well. So I'll touch on that actually on the next slide, just kind of planting the seed that ventilation does have a number of different impacts on a building's performance. Now, if we zoom in a little bit more to just residential ventilation, typically we're going to have an outdoor air or maybe an exhaust air requirement for the home itself, or if we're talking part 3 buildings, then each suite in a MERB, as well as the common spaces in a MERB. So corridors are a really common one. I'm sure if anyone's worked on a part 3 building, you're familiar, or even a part 9 MERB, you're familiar with corridor makeup air units. A lot of those buildings have amenity spaces, whether that's like a shared sort of lounge room, or sometimes gyms and those kind of things, which have very specific ventilation requirements. As I mentioned earlier, janitor rooms, mechanical rooms, parquets, those all those common spaces also have ventilation requirements. But just touching on the home for a second, so this first bullet point here, our older strategies and our older homes really use that strategy I was mentioning earlier of exhaust only, where we'd have an exhaust fan in the kitchen that people turn on when they're cooking, and then exhaust fans in the bathroom that would turn on if someone's having a shower or using it for other reasons. And then it sort of morphed a little bit more into some of those bathroom exhaust fans running continuously instead of just based on an occupant switch. But either one of those systems, whether it's intermittent or whether it's continuous, have the downside in that we can't control the incoming air. So if we're exhausting only, then the makeup air is coming in, generally speaking, through the envelope. And so, like I said on the last slide, that can have potential issues. So first of all, a lot of the times the air leakage is going to happen in places like around windows where there's a break in the air barrier. And so what this can cause is a thermal comfort issue. If, let's say, you've got a nice reading chair by a window, the exhaust fan's pulling air in and you're getting some drafts by the window. So that's the thermal comfort potential issue. And then you could potentially have other envelope issues because you're pulling in cold outside air. Excuse me. You're pulling in air, and just you could have the potential for moisture buildup at some point. Sorry, that would probably be more a summertime consideration where it's warmer and humid outside. But either way, ideally, you don't want to be drawing air in through the envelope where you have no control over that air. The other piece is that without having a dedicated supply air stream, we can't take advantage of preheating that supply air and using any sort of heat recovery. So that's where, like I said, we've seen this move towards more of a balanced ventilation in our codes and also in our building design. So we have both a supply and an exhaust that are equal. This gives us the opportunity to add heat recovery. And there's also ancillary benefits. So now that we have a supply airstream, we can actually filter the incoming air. This can lead to better indoor air quality just on a daily basis, especially if you have a building, near a busy road or maybe under a flight path or something. And then there's also better resilience. So as we see the increase in forest fires over our summertime, those buildings are gonna be a lot more comfortable for the occupants. So this flow chart is a really quick overview just to give everybody an idea of where our ventilation requirements are coming from. There's obviously a lot of detail in all the standards we're talking about, so we're really just kind of touching on them and just highlighting what standards are out there, because we are going to refer to a couple coming up in the presentation. So ventilation requirements in BC are stated in the BC Building Code, and there's section 6.3, which is in Division B, and that's where ventilation system requirements are described. First of all, they actually refer to a separate standard from ASHRAE, 62.1 2001, and that applies to all buildings. But for housing and small buildings, there's also a separate section, specifically 932, that talks about ventilation for those types of spaces. Now, this section has its own flow rate requirements, and then it also refers to another potential standard that could be used for sizing, which is a Canadian CSA standard F326. So again, super briefly, just touching on those two standards that I mentioned, the two external ones. ASHRAE 62, so like I said, it's called Ventilation for Acceptable Indoor Air Quality. It applies to all buildings and space types. And where we generally see is that it's not used within the home itself or a suite. It may be used for a corridor or amenity space, that kind of thing. So that's sort of where that one may tend to show up a little bit more. Whereas this CSA F326 standard I mentioned, if that were to be used, that's more for in the home itself or in the suite, in the unit. Now, we wanted to just highlight two other points within the code. And we've put the numbers there just so that it's clear. You can revisit this a little bit later on when you get the slides, if this one kind of triggers, oh, I should know about this. But we wanted to just mention them because it's where the step code shows up specifically in the ventilation section of the code and says, if you're designing a step code building, here's an extra rule you must comply with. So if you don't meet this, you could potentially put your step code compliance at risk. So that's why we just wanted to highlight them as kind of key. So the first one is that outdoor air has to be mechanically ducted to each suite, can't be indirect. And the second one, this is actually the one we've seen coming up on a couple of Part 3 projects that we then had to go say, actually, this design is not allowed under a step code building. But you may be familiar with some design strategies that will use a constant continuous flow exhaust fan in one of the bathrooms, usually the main bathroom, and then some sort of trickle vent either under windows, typically under windows, to make up the air coming in through like a living room or a bedroom. If that's a non-step code building, that design is allowed currently under BCBC, but that strategy cannot be used in a step code building. Even if you meet all the TEDI and the MUI and the TUI requirements, that strategy just is not allowed. So that's just one thing to kind of keep in mind if you're working on a step code project. The last thing from a ventilation design perspective is that some organizations do have their own specific requirements. And we wanted to bring up BC Housing as an example, since they are building so many projects right now in BC. So these are a quick snapshot of some of the ventilation requirements from their 2019 design guidelines and construction standards. So they say if you have a central HRV supplying multiple units, then there's a flow rate requirement based on the number of bedroom per unit. And if you have individual HRVs inside each suite, then there's a flow rate requirement based on the number of bathrooms. And those are generally fairly close to the requirements you'll see in 932 in the BC Building Code, but there could be a little bit of, it could be that one's a little bit higher, in which case you'll have to follow the BC Housing requirement if it's higher. So just again, something to keep in mind if you're working on that particular type of project. And since we're in the guidelines, we also thought we'd just point out that they also require a minimum 75% of sensible heat recovery. So again, just another good thing to kind of note if you're working on a project for them. So we're about to get into the interaction between ventilation and step code, but we wanted to provide them to you with some actual project examples. So we've got two here. One's a part 9, one's a part 3, and one is a low step code and one is a high step code. So first of all, here's our single family home. This is actually a very high level step code. Technically, it's a passive house, but that's equivalent to step 5 of the step code. It's in Saanich, which has a heating degree days very similar to Langley. So you may remember from Kevin's presentation, Langley's heating degrees of 2,700. We're just below that. It's about a 2,000 square foot home, 3 bedroom, 2 bathroom. And this is the a model of the home there. And then the part 3 building, this is a low level step. So it's a step 2 MERB located in Victoria. Heating degree is slightly higher than Langley, 2,750. It's a 5-story building. There's a 1 level of concrete with sort of some amenity spaces and stuff below, and then 4 levels of wood frame above. It houses a total of 72 suites and is just over 42,000 square foot. So those will be the two that we're going to use as we explain some of the examples coming up in the next couple sections. Okay, so how does ventilation interact with the step code? Just revisiting this table, I kind of alluded to this earlier on, but we're going to focus on these 2 areas, the equipment and systems and the building enclosure. So for those of you who have stuck around since the poll, so the answer there is the biggest impact from ventilation will actually be on the teddy, and we'll go through some slides on why that is shortly. And so the way that we've taken this finding and worked it into our process is that for residential buildings, we typically focus on trying to reduce the teddy as much as possible, or at least to get to the target requirement. And then we find that that will usually get the MUI and the TUI to pass. That's kind of been our strategy. So let's jump into how does ventilation impact the teddy? So I want to introduce you to our donut chart. That's what we call it. This is a graph that we put in all of our energy modeling reports. And this is an example, the one that I'm showing you here is an example from that step 2 MERB that I was showing you, so in Victoria. Now for that particular building, the teddy requirement is 45 kilowatt hours per meter squared per year. So what this graph shows us is the 3 big areas that are contributing to our teddy. So first we've got our ventilation here in blue. We've got the envelope infiltration here in green. So you may be more familiar with the term air tightness. We talk about infiltration and air tightness kind of interchangeably, but this is where the air tightness is showing up. And then this is the contribution to teddy of the envelope assemblies. So what is being lost through conduction? So obviously these two areas are really important as well. We need to get our air tightness nice and low, and we need to have a good envelope so that it's not causing too much heat loss. But of course, today we're really focusing on the ventilation side. And so in this example, we can see that roughly ventilation is contributing to about 40% of the TEDI. Now I should point out that this result that I've shown here, this is when we get a TEDI of 43.5. So this is at the end of the project. We've already optimized our design to make sure that we're passing and meeting the 45. But sometimes when we first run a project, we'll see the number way up above what the requirement is supposed to be. And so what we do is we actually use this as a tool to work with the team and say, okay, so where should we focus our energy, no pun intended, to reduce the TEDI? What's our low-hanging fruit going to be? So let's say if this were our example and we were trying to get down to the next step of 30, where would we focus? So I think ventilation would be kind of an obvious one to start with. Can we maybe get better heat recovery? Can we employ some of the strategies we're going to be talking about soon? And I think a lot of the questioning would come down to how much is that going to cost us versus, say, choosing better glazing or better walls. A lot of times, we know that throwing more insulation on a roof is often a really cost-effective way to get a better R value, but it's going to have a very minimal impact because that piece of the pie or the donut is already so small. So this really helps us steer our discussions to the areas of the potential highest impact. Just to share with you what we typically see just on the range of projects that we've done in the past. Ventilation is usually around sort of 25 to 50%, so a quarter to half of that donut. I would say that generally it's lower, so more in the 25% range for higher step projects, and that's usually because it's one of the more cost-effective strategies to get this number down, rather than, say, going to triple glazing or adding more external insulation or whatever the other options might be. So that is why we typically see ventilation having a really big impact on TEDI. But let's not forget, of course, that it also impacts MUI and TUI, so the mechanical energy use intensity and the total energy use intensity. So this example is still from our step 2 MERB, which has a requirement of 130 kilowatt hours per meter squared per year. So that is what this graph is showing us. On the bottom, our limit here is 130. And our project is achieving 123.7. So again, we're passing right now. This is the end result after our project was complete. So one thing I just wanted to point out is that we also show along the bottom what the requirements are for steps 3 and 4. And you can see that our project is actually a lot closer already to step 3, which is a limit of 100, and step 2. So this is kind of what I was saying before as how ventilation, our strategies kind of, if you work hard enough to get the TEDI down to the requirement, usually speaking, the MUI and TUI will follow along because it's not as difficult to achieve as the TEDI requirement. That's just generally what we found in residential buildings. So what do these different colors represent in our results? Well, that's shown in the legend down here. So the yellow is lighting, the red and the pink are heating for gas and electricity, and then we have fan energy and a couple of other end uses shown along here. And we just wanted to point out that, of course, ventilation is impacting the gas and the electric heating load because that outdoor air has to be heated up into a comfortable indoor temperature. But it also does impact the fan energy because the volume of air that we're going to be moving is related to how much energy our fans are going to require to run throughout the course of the year. So those 3 are not all due to ventilation, but they're definitely impacted by it. So those are kind of the basic metrics and where ventilation shows up for that one, that initial table that I was showing you. There is one other really important way that ventilation plays a role with both the TEDI and the TUI, and that's with respect to the corridor pressurization adjustment. Now this is a Part 3 adjustment, and it's something that's outlined in the City of Vancouver Energy Modeling Guidelines, and Jean actually referred to this earlier on, but if you're not familiar with those, I've put the little link in here where you can get them, and also highlighted the section that we're talking about right now, which is the corridor pressurization adjustment. So what this adjustment is for is it accounts for our local practice in BC of typically over-ventilating our corridors with respect to what the minimum code requirement is. And we do this because we're trying to prevent smell migration between suites in a multi-unit building. And so there's a recognition in these guidelines that by providing more outdoor air for a good reason, for preventing odor migration, it's going to have an impact on your step code results. And they didn't want to immediately penalize everybody for that. So this adjustment actually relaxes the requirement if you're pressurizing your corridor. So what happens is you design your building, you run your energy model and get your TEDI and your TUI, and then you do this separate calculation to figure out what your corridor adjustment is. And then you get to subtract that adjustment from your result. So you reduce your TEDI or your TUI by whatever the adjustment is. And I'll just show you that in just a second, a slide or two. I'll give you an example. There is a limit. The adjustment can only be up to 10 kilowatt hours per meter square per year. But when you think about it, the TEDI requirement for, say, a step 4 building is 15. So that can actually be a really big impact. Technically, your result could come out of the energy model at 25. If your adjustment hits the max of 10, you would subtract 10 and you'd pass the requirement of 15. So that's pretty big impact on your results. And again, I'm not going into the details of the adjustment, but it's based on the pressurization airflow, the area of the corridor across the whole building, the area of the whole building itself, number of units, and heating degree days. So it does take into account climatic considerations. So here's that example, looking at our step 2 MERB that I introduced to you earlier. So let's say we followed code to the letter for this particular building. So we're going to take our ASHRAE 62 minimum flow rate, and over the course of our whole building, which is, remember, 5 stories, we're going to have 1 makeup air unit on the roof at 160 CFM. So that results in 2 CFM per door. So anyone who's worked on a building like that would know, first of all, that's a really small makeup air unit, and that's way lower than the kind of airflow per door we would typically see. Usually, I would say, just having seen a lot of mechanical engineers' designs, we usually see in the range of sort of 5 to 10 CFM. Back when I first started designing, I'd say we all just target closer to 10, but some of that is coming down a little bit, but still I haven't ever seen designs quite as low as 2. So for this building, what we actually saw once the design was complete is that the mechanical engineer designed the the unit to serve to provide 680 CFM, again over the course of 5 floors, which averaged out to about 9 CFM per door. So a lot more typical range that we're seeing, but of course we're now being penalized for a lot more outdoor air that we have to heat. So that's going to really impact our TEDI. So remember, our TEDI requirement for our project was 45. So when we ran the original model with that full 680 CFM flow rate before any adjustment, we were actually failing the TEDI. We came out at 48.4. And that's largely due to that overpressurization, overventilation in the corridors. We then ran our adjustment calculator and it came out at 4.8. So we could then subtract the 4.8 from there and we get a result of 43.6. So now our TEDI passes. And that's completely legitimate way of approaching it. That's in the City of Vancouver modeling guidelines. So I just want to make one note just kind of reiterate one point, that this is only on the pressurization airflow that's delivered to that corridor. So if you, for example, have a corridor where you're supplying 150 CFM, and then maybe you have a janitor room on the end that's exhausting or returning 50 CFM to a central HRV or something like that, the adjustment is only going to apply to that 100 CFM that's being used for pressurization. So it's just one thing to really keep an eye on. We've seen a couple projects get tripped up on that later where they thought they had a bigger adjustment because they used the whole makeup air unit airflow, but then once they reduced and got rid of the exhaust, they actually, the adjustment was a lot smaller. So just something to be cautious about, basically. Okay, so we talked about how ventilation really shows up in the TEDI and the TUI, or TUI or MUI. So now we want to talk about and share some key strategies that we've seen to really help focus reducing those numbers, especially the TEDI in both your Part 9 and Part 3 buildings. Okay, so strategy number 1, don't overventilate. We noted that this applies to all spaces, so it's not just corridors, also inside the suite, inside other rooms as well. And I realize that this may seem like an obvious one, but when you consider sort of the steps that go along the way from original design to construction and operation, there are a lot of places where sort of safety factors are added and overall rates can really easily creep up. So just consider, for starters, we start with a very conservative calculation. So our ventilation has to be for maximum occupancy. And most of the time, our building is probably not going to be at maximum occupancy. Then likely there will be a safety factor added to that calculation. And there may also be some rounding up to the nearest, 10, 20, 50 CFM, however people are working it. And then once you've got your rate for each space, you have to select equipment, and likely you're not going to find a unit that delivers the exact rate that you're looking for. So you'll have to select up a unit size, and that's going to add in another buffer as well. And then we'll touch briefly a little bit later on testing and balancing. But again, oftentimes folks will come in and go, well, if I can't quite tune it to where I'm going for, I'm going to err on the side of caution and use a little bit of a higher number. And that can sort of just compound, again, that increased flow rate. And so you can often start with a number and end up with, being 1/2, 2 times what that original number was when you start to add the compounding effect of all of these different calculations. So again, just something to kind of keep in mind is trying to keep ventilation rates close to design. We don't want to underventilate. We obviously have to meet code, but trying not to go overboard too much. And we'll talk about a few control strategies as well later as to how to keep ventilation rates where they need to be when they need to be. So that's strategy number 1. The second one probably comes as no surprise to anyone, but really using good heat recovery. So I think it's fair to say that pretty much every STEPCO project we've seen has had heat recovery. We've put in a couple of suggested target efficiencies below based on what step you're trying to achieve. These are by no means a pass-fail. If you hit this number, then you will get there, but they're definitely a good starting point, certainly if you're in early stages of design and you want to just kind of get a feel for what should we be aiming for. And then just a reminder, as I mentioned earlier, there are some jurisdictions or some organizations that have their own requirements, such as the BC Housing minimum 75%. So in that case, if you were working on a BC Housing Step 2 building, you wouldn't be able to use the numbers that we've got shown on the screen here. And then I wanted to show you one more way of looking at the TEDI that really touches on those first 2 strategies, so not overventilating and using heat recovery. So this is another graph that we really like. And this is actually one, I should say, we borrowed the look of it from the Passive House software. So if anyone's familiar with Passive House, that you may recognize this. We liked how it kind of communicated things, and so we developed our own version of it as well. So what this graph is looking at is it compares the losses and the gains that ultimately make up the TEDI. So remember our donut chart, we had ventilation losses, infiltration losses, and then envelope conduction losses. So those add up to a certain number. And then on the gain side, we have heat recovery from our ventilator. So that's a pretty big gain. And then we have other things inside the building, like fan heat pickup, plug loads, occupants lighting, solar gains. And then anything that cannot be made up through these gains, that's what our TEDI is going to be. So if we run a first analysis and our TEDI is too high, this is another graph we can use to say, okay, well, what can we do? We can either reduce something on the loss side, or we can increase something on the gain side. Now, some of these are going to be restricted by the code, by the modeling software, or not software, the modeling standard that we're using. So we can't, for example, go in and say, well, I'll just put twice as many people in my building and my gains will double. That's not allowed. So we have to focus on the areas that we're allowed to adjust under the modeling code. So that's kind of the overall introduction to this graph. Now, if you remember back at that donut chart, I said that the ventilation was about 40% of the TEDI. That's after heat recovery. So that first graph, the donut one, just showed us from here down. So that's where the ventilation was about 40%, infiltration was maybe 20%, and then the remaining 40 was conduction. What this graph shows us is what is the actual overall loss due to ventilation before heat recovery. So you can see here that the ventilation is actually the biggest loss in our building right now. We do have the fact that we've got heat recovery is great. It brings our ventilation down. But what this does show us is that there's actually more heat recovery opportunities available. So right now we're recovering, my guess would be maybe we're at about a 60% unit. If we got a higher efficiency unit, that would start to creep down, and so our TEDI would get down lower. So again, this is kind of just a helpful way for us to take a look at the big picture and just say, where's our low-hanging fruit? What's currently the biggest losses, and start to really play around and sort of iterate how we might be able to improve our results. Okay, so there's a third strategy I want us to share, but before, that's actually on the next slide. Before we get there, I just want to introduce what is the strategy, which problem is the strategy trying to fix? And in order to do that, we have to consider that when you're dealing with a multifamily building, a lot of times the question will come up early on, do you want to use local units in suite, or do you want to have one central heat recovery ventilation unit that's supplying the whole building, or at least multiple groups of suites? So we'll just talk quickly through the pros and cons of those systems before we get into the sort of strategy that I wanted to share with you. So first, let's just talk about if you have an in-suite units, so one, say, HRV within every suite, and some of the pros that come with that. So first of all, for billing purposes, it's much easier to bill everybody if their own unit is showing up on their own electricity meter, rather than trying to divide that out per unit. Another pro is that you will have less floor area lost to shafts that are accommodating ductwork going between floors. Similarly, when you have a central unit, whenever you have penetrations going from one suite to another, or from the corridor to a suite, you're going to have fire or smoke dampers. And so that can start to get expensive if you have that at every single suite. An in-suite unit does not require those dampers, assuming that HRV is only serving one unit at a time. And the last pro for in-suite units is that you get better individual suite control. So if someone's cooking and showering, they can usually flip a switch, and that will increase the exhaust rate for that room. And that will also increase the HRV supply rate. So you're still getting balanced airflow in that particular unit whenever you need to have more exhaust from a room. So that's for the in-suite unit. And then, of course, there's also some pros to central units. So especially if you're dealing with a rental building where you have one operator or one owner operator, you'll find that central unit, or even if you have, say, 3 rooftop HRVs that are serving a bulk amount of units, you're going to have a lot less maintenance if you have a single unit. So filter changes, fan maintenance, all that kind of thing will be a lot easier if you have fewer HRVs. From an energy performance, you'll also have fewer penetrations through the envelope. So the in-suite requires 1 supply duct and 1 exhaust duct per suite, whereas the other one doesn't have as many. And there's the potential for fewer drop ceilings in suites. That's not a done deal. But again, because you've got the HRV in each suite in the first scenario, oftentimes you may need a lower drop ceiling to accommodate that unit. Or if you've got more ductwork running around in the suite as a result, then you may require more drop ceilings. So that one's kind of on the fence, but we just thought we'd bring it up still as a possibility. Now what we've seen is the biggest con to this central system is providing that individual control that I mentioned over here. Because if you've got a 50 unit building and someone in unit 10 starts to cook, and so they want to increase, or takes a shower and turns on the bathroom exhaust fan. Now, first of all, you're telling the unit at the top to increase by a small amount because it's sized for a much larger overall airflow because it's serving so many units. And then secondly, you have to also increase the supply airflow again by a very small amount. And with different, having say 50, maybe 100 suites, turning on and off their fans or trying to bump up the exhaust flow rate for different periods of times, it can start to get really complicated control-wise. And we've seen some designs that use pressure sensors to try to balance that out, but that can also get costly because now you're installing pressure sensors everywhere as well as controls, and it can just kind of get complicated and costly. So the strategy that we wanted to share on the next slide is to sort of address this issue if you're considering a central HRV, but you're concerned about control. Okay, so first of all, let's just consider that that original scenario I was describing, where you have an HRV running, let's say it's at 60% of the peak rate, and then 3 times a day on average, it gets bumped up to 100% for an hour when people are showering and cooking and whatnot. So that's that first, that's what we've graphed first in the background here in blue. Now instead, if you wanted to do a central HRV, if you oversize it slightly, so you're running it continuously, instead of at 60%, you run it at 65% throughout the day, in the end, you're actually going to get the same daily airflow. If you do the numbers, they come out to the same overall airflow. So essentially, you're still getting that same air movement. You're actually going to end up with generally better air quality and more consistent air quality throughout the day. And then, of course, if you decided that maybe 5% wasn't enough, you could potentially go a tiny bit higher to 70% or choose another number that worked for your project and still meets your TEDI requirement, which actually gets you better air quality than this scenario here. So we've seen this on a couple of MURBs that has gone through design and construction, and they've just started operating since, the step code's only really 4 years old. It's taken a while to get too many projects that are running full time with them. But so far, it seems to be a strategy that, that works fairly well. Okay, so our fourth strategy is really focusing on corridors. And we just wanted to just share a few thoughts around corridors, since, as I showed you before, they can have a really big impact, especially on the teddy. So first, you want to follow those kind of first couple strategies we already talked about. So the one about reducing air volumes is important. Now, first of all, I've already explained that oftentimes we do overventilate. So how do you find that kind of sweet spot where we're providing some pressurization for odor control, but we're not totally overventilating? So what we're suggesting is that if your adjustment, that corridor adjustment, is over the limit of 10, you've probably gone a little far. So maybe pull back your corridor ventilation flow rates in that scenario if you're exceeding the limit of 10. So that's kind of our tip for corridors and overventilating. As far as adding heat recovery to corridors, it's definitely a great possibility for improving your teddy. But just remember that this is going to impact your corridor adjustment, because if you started out with a scenario where you're just pressurizing and now you're doing heat recovery, so you've got the supply and the exhaust, then your pressurization air volume is going down, and so your corridor adjustment could also go down. So just be cautious if you're using this. Sort of maybe run the calculation once or twice just to make sure that you're not inadvertently penalizing yourself. The one solution we've seen that does work is if you have a central system for delivering a whole bunch of suites, then you have the option to also preheat the corridor air, but don't return air. So it's still pressurizing the corridor space, but it's not recovering heat from the corridors, which means that you still get the corridor adjustment, but you also get the benefit of getting a little bit of preheat if there's any left over from your suite central HRV. So that's kind of another tip you can think of for your corridors. Another one that we advocate for is just reducing the set point temperature a little bit in those spaces. So in corridor, generally acceptable to reduce the set point temperature, say, to 18 degrees instead of a fully conditioned 20 degrees in the winter, because people are, generally wearing their outdoor jackets and stuff as they walk through corridors, and they're not sitting there for long periods of time. They're not fully occupied spaces that way. And then we wanted to touch on the concept of external corridors. We have seen them on some projects, and they can be a little bit of a plus or minus. So you want to be really cautious when you consider them. The benefit is that because you're now outside, you don't have any ventilation requirements. So they're not going to add to your teddy, but they do have other implications because the corridor area gets used in the teddy calculation. And so by reducing the overall building area, when you're dividing by the teddy, or by the area for the teddy or the MUI or the TUI, now you're dividing by a smaller number, so it can sometimes make it harder to reach the teddy, MUI, TUI target. You also could have the potential to lose your corridor adjustment, you would lose the corridor adjustment factor, because if it's outside, then you're not allowed to calculate that. And finally, we've seen some other interesting implications in that, like, every suite door all of a sudden becomes an exterior door. So now you have to have a much higher R value for that door. There's air tightness implications, things like that as well. So it's a possibility to consider external corridors, but it's not a cut and dry solution that will get you across the finish line. So plan it early on and think about it. It could work for your project, but it also could pose more challenges than you'd intended. And our last strategy that we wanted to share is for when you're trying to achieve these higher steps. Sorry, my my laser pointer is stuck. So this is where we wanted to share with you a common strategy that we've seen on most passive house projects that can easily be adapted for higher steps as well. So this is where instead of having just a dedicated exhaust from the kitchen hood, you use your HRV to supply to living spaces as you usually would, bedrooms, living rooms, and then also exhaust from bathrooms and kitchen and run those continuously. So you have constant exhaust coming out of those spaces and constant good airflow. Now for bathroom, you can still have your controls for increasing if someone's having a shower. And then for kitchens, you still have this constant exhaust. That's what this little exhaust vent is showing up here. And you also, but use a recirculating hood. So you want a two filter approach for that, a mesh filter that will help remove any sort of water vapor from things boiling under the stove, and a charcoal filter for odor removal. Now, I know a lot of people get a little bit cautious when they hear recirculating hoods. We used to live in a heritage home, and it did not have a direct vent exhaust. It didn't have anything when we first moved in. So we put in a recirculating hood, and we actually found it worked pretty well for what we needed. You know, we tend to cook mostly just in the evening, have stuff on for maybe half an hour to an hour. And it served what we needed quite well. So won't work for every application, but definitely a strategy that you can consider, especially if you're trying to get through to higher levels of the step code. Okay, a couple of other considerations. I've been using the term throughout HRV, which stands for heat recovery ventilator. There are, of course, kind of sister units, energy recovery ventilators. So just wanted to touch briefly on the difference between the two. An HRV is going to be for sensible heat only, and it's pretty much good for the Lower Mainland in most applications. The kind of downside to an HRV is that on cold days, on the heat exchanger, and it depends a little bit on the heat exchanger type, but you can get moisture buildup within the unit. And so that's going to require a condensate drain and some sort of additional plumbing. Sometimes the unit will hang a little bit lower because you might have a tray underneath to capture that condensate. So sometimes people will shy away from an HRV just because of that reason. An energy recovery ventilator captures both sensible and latent heat from the exhaust airstream into the supply airstream. So that's basically, it allows for some moisture transfer between the two airstreams. A benefit is that it can prevent air from getting too dry in the winter, which is kind of more of a cold climate consideration. It's not probably as relevant in Langley. But we should be aware that in some sensitive applications, you can't use an ERV because of particle transfer between those two airstreams. So if you were exhausting from you know, a janitor room that has some chemicals in it or something, you may not want to run that through your ERV because there could be some, you know, particle transfer that you just don't want to get into your supply airstream. I did want to just highlight, though, that both an HRV or an ERV would realize the benefits of better energy efficiency and better indoor air quality over exhaust only. So those you don't have to worry about when you're trying to select between one or two. Now, so far we've really been talking about design considerations, but of course in real life, how the unit is constructed, installed, and operated is going to have a big impact on utility bills. So I alluded to this earlier, but it is important to test, balance, and commission the system to match the original design. And so this would involve checking that airflows are correct. So both in the space, but also at the unit, because that way we're making sure that we don't have any excessive duct leakage along the way from what's being taken in at the unit and then finally supplied to the spaces. If you have an HRV or an ERV that's got some unique features, such as that sort of low continuous rate and a high rate, then it's important to test them at both rates. And then also, a lot of these units will come with bypass mode. So in the summertime, you don't necessarily want to be capturing heat from your exhaust airstream and putting it back into the building. So a lot of units will come with a bypass where when you may have the option for free cooling, you can actually just bring the outside air right into the suite. So if you do have bypass mode, then you want to test and make sure that it's working as well before handing the building over. And on that note of handing the building over, it's always helpful to provide a manual to the owners. So explaining those things, if there's bypass mode, if there's preheat that they should be aware of, how frequently should filters be changed, and any sort of other maintenance considerations that you may want to highlight, especially if the users are new to this type of system. You know, if it's a homeowner who's never had an HRV before, or building operators who aren't used to maybe an ERV and how that might look, for example. So as I said, we'd touch really briefly on commercial buildings. And it's great, sounds like Langley's going to be consulting soon on whether or not to bring commercial buildings into the STEP code. At the moment, commercial buildings that have STEP code targets are office, retail, and hotel buildings. Public sector buildings have also been wrapped into STEP 1, but they don't have any TEDI or TUI requirements beyond that yet. So that's just kind of the building typologies that we're talking about right now. But these strategies we're talking about could also apply to amenity spaces within MURVs. So I just wanted to make sure that we're talking about that too, those spaces along with commercial buildings. So we really want to start with the same strategies as before. Don't overventilate, use heat recovery, and if possible, lower the heating set point. We talked about that before in the context of corridors, but in these types of buildings, you know, maybe you have a lounge that's a shared amenity space that's available from 6 a.m. to midnight. Then you can have a setback temperature at night when the lounge is locked and unavailable, and that will help save energy and reduce your TEDI. So it may not be a constant set point, but using setback strategies and those kind of things will help your TEDI. Another ventilation option is demand control ventilation. So this is only providing outdoor air when it's needed or when it's demanded. It tends to be most useful, most applicable in spaces that have varied usage. So let's just go back to that amenity room. Even if it's available from 6 a.m. to midnight, chances are people aren't using it for that full amount of time. So if they have a carbon dioxide sensor in there that helps track how many people are in the space and only provides a minimum ventilation throughout the day, but then ramps it up when there's more people in the space, that will again help your TEDI. And the modeling guidelines, the Vancouver modeling guidelines say that that's an acceptable strategy too that can be used for reducing TEDI. One other one to keep in mind, we see a lot of buildings that have, say, commercial kitchens. Again, those ones can be really harder to heat recovery off of because you're going to have really high ventilation requirements anywhere you're cooking with gas, and you're not allowed to put like a heat recovery coil or anything in the exhaust airstream just for fire safety reasons. So what we've often come to the conclusion, or the kind of design that we tend to lean towards, is again having one system that kind of provides continuous background ventilation, and then when the gas cookers are on and that range hood is exhausting a lot of air, have a separate makeup air unit that will supply makeup air and has a really efficient heating system. So maybe a heat pump system, and it's only on when those gas cookers are on and those range hoods are on. So you're still balancing the ventilation, but you're only providing it when it needs to be provided, so on demand. And finally, if you are a building owner, then you can consider sub-metering your energy usage. So like I was saying before, you know, this is the real world. How much energy is my building actually using? Is my corridor makeup air unit running properly? Those kind of questions will actually get proper energy and cost savings versus just the design side of things. If you're looking at reducing greenhouse gas intensities, generally speaking, all the strategies we've talked about to this point, anything to reduce the TEDI, the MUI, and the TUI, those are pretty much also going to reduce your greenhouse gas emissions. So those are all still on the table if GHGIs are something that you're keen on. A couple of other things you can also consider. First of all, if you're using gas units, then choose the highest efficiency you can. So get a condensing boiler or makeup air unit instead of a regular one. And then, of course, any sort of fuel switching from gas to electric is going to result in greenhouse gas emission reductions. So we've seen that recently on a lot more corridor makeup air units with electric heating coils, also boilers and backup boilers for hydronic heating systems. And recently we did some costing with a cost consultant, and they were showing how electric boilers were coming in cheaper than gas for the equivalent size. The caveat is that we'd want to make sure you look into what kind of impact this is going to have on your electrical service. And then, of course, finally, moving to renewables is a clear way of really reducing the greenhouse gas emissions. And there's, renewable natural gas, and then there's steps beyond that with solar and wind and those kind of things as well. Okay, so just wrapping up here, the kind of key messages we really wanted to leave everyone with is that TEDI is going to be, generally speaking, the hardest Part 9 and Part 3 metric to meet. And ventilation is one of those big 3 contributors. So remember the donut. Reducing ventilation is really generally an easy win. And when we say easy, we also mean cost effective. Keep in mind too that addressing the TEDI will usually get you, it will improve the mewing, TUI, and GHGI, and usually get you to the requirement you need to hit. And the key strategies that we shared, don't overventilate, so that's both on the design and the control side. Use good heat recovery. We shared some special strategies for corridors, for sort of unique spaces and higher steps. So do revisit those, check them out if you're working on a space like that. And then build well, balance, commission, and maintain. A couple additional resources we wanted to share, and the township also had a lot of these on their website. The Part 9 handbook for building officials, sorry, these are all from the Energy Step Code website, so that's the link at the top of the page. There's a handbook for building officials with a section on ventilation, and it's got some design examples, so we wanted to flag that one. Jean talked briefly about the Part 3 Energy Design Report. That includes a corridor adjustment calculator, so if you're uncomfortable doing it yourself, download that Excel spreadsheet for free, plunk in the numbers that it's asking you for, and it'll calculate it for you. So that's a good one to know. And finally, there's a Part 3 Step Code Design Guide and Supplement. And again, that has sections on ventilation systems and strategies if you're looking for more information. And that's it from us.
Thank you so much, Susan. That was really great. I think we all learned a lot. I think we have some time for some questions, so I'll look through the chat here. And while I'm looking here, if anybody in the attending has any questions, just plop them in the chat, and I'll come to them there. So Susan, I have a question from Andrew, and he asks: to meet step code, must you install an HRV/DRV starting at step 3?
Yeah, it's a tough one to say. I would say that, oops, sorry, I'm just trying to actually be able to see you there, but that's not seeming to work. I'd say you probably want to start with a step, with a HRV from step 1 most of the time. It's not guaranteed, but it's really highly recommended.
Okay. Thank you, Susan. And
there we go. Sorry, now I can see. Okay.
Okay. Wally asks, how about a manually operated makeup air close to the kitchen exhaust hood?
Yeah, that's a great idea. That's the kind of strategy we were trying to suggest for when you have those range hoods that you have to turn on, is to have another makeup air unit that's tied into it. The only thing is, I'd say maybe don't we've seen it where it's connected so that they just have to turn on the exhaust hood and they don't have to then again turn on the makeup air unit manually, but so have them interlinked control wise. But yeah, that's exactly the idea. And then you can have a really efficient heating system for that, but it's not running continuously. It's not as expensive because it's only for the makeup air. Yeah, definitely.
Okay, great. We have a question from Willow. Does ventilation have that much of an impact on HOT 2000 energy modeling?
Yeah, so I mean, the ventilation will have an impact on the model regardless of what software you're modeling it in. Those results that we were showing you weren't from HOT 2000. They're ones that we take out and put in Excel and we kind of fiddle with ourselves. But if you were to pull out the HOT 2000 information and then kind of plug them through our spreadsheet, you would see similar results there as well. So yeah, it's important for both part 9 and part 3.
Well, I don't see any more questions coming in directly for Susan. There seems to be a few questions for Ajeen, and he will address those via email. So I think we can start wrapping things up. I'll share my screen now. Okay, well, thank you so much, Susan. And for all of you on the phone, so just a reminder, you have access to credits here for BC Housing. You don't have to do anything. Sarah is going to send you your proof of attendance, and you can use that to register your points, your credits. For those who need AIBC credits, nothing you need to do. We track credits. Sarah is going to send the list to AIBC, and they'll credit you. So a big thank you to Susan and Wes at Focal Engineering. We really appreciate all the great information and answering those questions. Also to BC Hydro and Fortis BC for sponsoring this event. And of course, a big thank you to all of you for attending. You are at the forefront of energy efficiency and emission reduction, so thank you. Some notes for those of you who couldn't hear or had some audio issues. It seemed like that was a bit of an issue there. We will have a recording available and slides for a limited time, so please reach out to us to have access to that, and we should have that on our website, I believe, as well. Anything compliance related, you met Ajeen today, so please reach out to him. We have an email address here, greenbuildings@tol.ca. You can just email that, and we'll be able to direct you to the right people. Again, if any talks about heat pumps or ventilation seems a little bit unfamiliar to you, please visit our website at tol.ca/step code to access our previous Builder Forum series, and we have quite a bit of information there on building science, mechanical systems, etc. So please visit that. Also, as Sarah Maleska noted, we will be having a follow-up email with other answers or any details from this webinar, but also you'll have a link to a survey. Please take roughly 5 minutes or what it takes to fill that out. We need that data to help inform our future sessions and as well as see what's working for you and what we can improve on. And lastly, a big thank you from the Green Buildings team, and that's Sarah Maleska, our technical assistant, Jean Surendran, our building energy specialist, myself, Kevin Ramley, Green Buildings manager, and Robert Baker, our assistant chief inspector. Well, thank you for your time today. So with that, I will let you go right on time. So thanks, everybody.